College Autonomous, Thrissur.
Sure.
Thank you, sir. Thank you for accepting our invitation and coming for the webinar. I think we can start the program shortly.
Yeah, sure.
I would like to call Swarna ma'am, who is the HOD of our department. Please unmute. Swarna miss?
Yes, Anjali. Yes, Anjali. Yes.
Yes. So we shall start the program right now.
Okay. We'll start. Welcome, Harivarma, sir.
Yeah, hello, madam. Yeah, thanks.
Arya?
Yes.
Swarna miss, I think you can mute your phone. Yeah. Yes.
So can we start?
Yes, you can start.
So good afternoon, everyone. Today is the 5th day of our webinar series. Today we have the session on the role of mathematics in medical imaging. The session will be handled by Dr. Harivarma, the Assistant Professor of IIT Bombay. So we can start the program by a silent prayer. Thank you. Now I welcome Ms. Divya, Assistant Professor of Vimala College, Thrissur, for the welcome speech.
Good afternoon, everyone. Warm greetings to one and all. On behalf of our college, I extend a very sincere warm welcome to all of you present here on the webinar series. And it is a great honor for me to introduce and welcome today's resource person, Dr. Harivarma, Assistant Professor, Department of Bioscience and Biotechnology, IIT Bombay. He is an accomplished person with several published works to his credit. During this motivational journey of his hard work and achievements, the main golden feathers are Ramalinga Swamy Re-Entry Fellowship Award achieved in 2014 and earlier Career Research Award in 2016. Today, we are privileged to have an opportunity to listen to him this afternoon. On behalf of all gathered here, I welcome you, sir, to this platform. Once again, I welcome all the participants who present here. Thank you all.
Yeah. So shall I?
Yes, sir.
Yeah. So thanks a lot for the introduction and also for inviting me for this talk. So it's for the first time I'm going to talk to I think 58 or 66 mathematicians. It's going to be a very tough job for me. So first of all, I'm not a mathematician. I work in, even I cannot call myself as an applied mathematics person. I do some maths, and I was trained by a mathematician, Professor Nandakumaran at IISc. And my PhD supervisor, Professor Vasu, and Professor Nandakumaran was my co-supervisor. So Professor Vasu, who was my primary guide, he was also inclined to mathematics. So that way, what should I say? It's like I like mathematics, and I try to apply mathematics in my field. So that's the only relation I have. And I have, I think I have some exposure on how to use some sort of an applied math, mostly into PDEs and all into our problem. So that those things I can share. But I'm not very sure how much deep I can go into these subjects, which is not my primary area. But I can give a glimpse of what can be the role of a mathematician in this type of field. So that's a primary. I mean that's how I think I can talk to this audience. All right. So this particular slides that I have prepared is actually somewhat similar to what I have given for another FTP. But the idea is that the beauty of this subject is we can talk the same slides in two different ways. I mean, with respect to the mathematical aspect of this problem, with the same slides, I can stress that part. So you may see this slide in some other place, but then the idea is that the way in which I talk will become a bit different. Right. So I think I should start sharing the slides. So let me see how. I always, present now. So can you see the slides?
Yes, sir. Yes, sir. It's coming.
Yes. So it's in the full screen, right?
Yes, sir. Yes, sir. We can see.
And is it moving?
Yes, sir.
Fine.
Yes, sir.
Fine. So the title is Role of Mathematics in Medical Imaging. I think I have got some 80 slides or something. So in some places I will go a bit faster. The idea is that, as I told you, I will try to stress the importance of mathematics in medical imaging and what can be your role if you want to have a change in your field from your from the mathematics like your pure or applied maths to a more what do you say, applied or computational mathematics area, so that I can give an idea about what you can do. So as she told, I'm an assistant professor in Department of Biosciences and Bioengineering at IIT Bombay. So we run a lab, theoretical and experimental bioimaging. Although I say bioimaging, I do not look at cells or bacteria or like that. I'm not a biologist. I'm not a mathematician, but I work in bioscience department. So the idea is that it is something called this interdisciplinary PhDs, right? So nowadays people hear about it. So I did an interdisciplinary research after my BTech, and finally I got a job in bioscience department, and I do medical optics. That means developing imaging technologies for in vivo human studies. In vivo means we are like CT scans or MRI, where you do not take any samples out of the human body, but you have to do it in live humans. So that sort of things that we do. So let's go to different imaging modalities. So it may be difficult for you, for the people from your background to look at what do you mean by imaging or image processing for that matter. But these imaging modalities, I'm sure you will be familiar. So for example, ultrasound, of course, you know, MRI, CT scan, or this X-ray images that we usually take for some fractures, or it can be CT scan of the head like that, right? And maybe some of the technologies we may not be very familiar, like OCT, optical coherence tomography. Nowadays, people use it for eye imaging. Then there are fluorescence imaging, photoacoustic imaging, near infrared imaging, like that. So there are several types of imaging systems, right? Now, if you look at these imaging systems, so the main problem with these imaging systems are not the problem. The major difference between the imaging systems are they are based on different physical principles, right? So, say for example, if you look at ultrasound, it tells you how this ultrasound interacts with the tissue, so that interacted wave we can measure it and try to create some images of the object we would like to look at, right? So basically, we have to look at how ultrasound interacts with the tissue. But if it is an MRI, we have to see how this magnetic field and the radio frequencies interacts with the tissue, right? It's completely different. If you look at near infrared imaging, we have to see how light interacts with the tissue. If you look at photoacoustics, we have to see how the sound waves can be generated using light in tissue, right? So if you look at all these physical principles behind these different imaging systems, they are completely different, right? So the question is, the major difficulty that in biomedical imaging we face is to teach and also to learn these seemingly different imaging modalities, right? So because the physical principles are different, the instrumentation is different, because MRI requires huge magnets, whereas ultrasound doesn't require that much instrumentation, but it has got several other set of instruments needed, right? And the things that it actually looks at is different. I mean, MRI will give you some other parameter, mostly structural, whereas near infrared imaging can give you some physiological images. So all these things are, physics are different, what it looks for is different, the instrumentation, that means the machine, is different. But then how do you learn all this stuff if somebody wants to work in medical imaging, or how do you teach these things? So this is a big problem. And then the idea is that here mathematics comes to help us. So we can look for, we can ask this question: is there any common concepts which is there any set of concepts which actually common to all these imaging modalities? So this is a question that you have to ask, and that from that point, the role of mathematics starts in imaging, right? So this common platform with which we can actually study all these seemingly different imaging modalities, and that common platform you can actually view from a mathematical viewpoint, and there are in that platform actually mathematicians have some role to play, right? So that's what we are going to look at. So in order to look at that one, so we are going to look at so it's imaging. So let's start with an imager. So if you look at this picture, you can see there is sun, and the sun, and there is a pole where a bird is sitting, and I can see it from the other side, or this is actually a photograph, so I just photographed it using a camera, right? So what happens here is sun actually sends some rays, which is sunlight. It interacts with the object and the pole, and finally some rays is being captured by my eye or the camera, which contains an intensity contrast, which actually gives you this picture, right? So some part of the sunlight is being blocked by the bird and the pole, so that part will appear dark and the rest of the part will appear bright, and that's actually what this image is, right? So there are three things here. One is a source of some energy, and here the energy is light, right? Sun is a source, and then this particular energy interacts with the subject is the pole and the bird, right? And then after the interaction, this light is being picked up or measured by a detector. And what is a detector? Either your eye or a camera, right? So these are the three things that is involved in this image, generating this image. One is the source, one is the subject, or the material that you want to study, or the material whose images have to be generated, and then a detector for measuring the energy which is being interacted with this object, right? So the energy from a source is being utilized to generate images of a subject, and detector is here the light is the case, is the source, the energy is light, so we need an optical detector, which is an eye or a camera, right? And then if you look at it, you know that it is a bird sitting in the pole. So how do you understand that? I mean, I don't have to actually explain it, right? So the idea is that from our learning process, right, from the childhood onwards, we are learning many things, and it's being stored in the brain. So the moment you get this image in the brain, it can interpret. So you can do a post processing and then interpret that, okay, this is a bird sitting in a pole, right? So there is imaging happened, the images are being generated, and it is post processed in the brain to identify what is there in this image, right? So this is essentially what is being done in imaging. So let's have a look at this particular slide where it actually being explained. So you can see there is a probing wave which interacts with the object, and the interacted wave is being picked up by some detectors, and that will generate an image. Now this image need not always be visual image. It can be some other image. So for example, if you look at thermal images is nothing but what? It's a temperature distribution of the human body, right? Or it can be something like a proton density image or T1, T2 relaxation. So I'm not going to, don't worry about those things. So it tells you that in an MRI, what we actually show is a proton density. So it is nothing like we can visualize with our bare eyes, right? It is some sort of a different quantity being shown in a three-dimensional space. All right, so the image need not always be what we can see, but you can view it as some distribution of a function in a three-dimensional space. That distribution will represent some physiological property of the human body. If it is for example, I can show the three-dimensional distribution of the blood flow concentration in the human brain, right? So that is just a number. It's a function of it is the blood flow distribution is a three-dimensional function being plotted, and then you can visualize it. So where is the higher flow, where is the lower flow, like that, right? So that's all it says. So its image need not always be visual. It can be some property of the object. So the idea is that a probing wave interacts with the object, and the data is being collected, and from this data we want to find out some property of the object. right, which is relevant to us. And the object can be humans, animals, bacteria, cells, materials. So, for example, non-destructive testing, or in airports, we check our baggage, right? So that is again an imaging, right? So it need not always be living organisms. Now, so as I told you, the source can be anything. So depending on, so if you look at the electromagnetic spectrum, depending on the wavelength, we have different imaging modalities. For example, if you use radio frequency, we have MRI. MRI utilize radio frequency for imaging. Then we have microwave imaging, infrared. In fact, near infrared rays are used for imaging in diffuse optics or near infrared spectroscopy. Visible, that means the light that we actually see with our eyes, are used in microscopy. And then you have X-ray, which is used in computer tomography, like what CT scans and all what we are familiar in the hospitals, right? So depending on which wavelength you use, we can have different types of imaging modalities. Now, let's come back to the point from the viewpoint of a common platform, which I told you earlier. So let's have a simple experiment where I have given you a black box, and I have given you another information that there is a hidden object inside it. Now, without opening it, that means without hammering it or without destructively testing it, you have to basically tell me what is inside. So what will be your first response? So the idea is that the moment you get a black box with this hidden object, our first instinct will be to look at it, right? So if there is a source of light, we may even show against it and see whether we can see something inside, right? So what actually we do is we are trying to get an external source of light, which is ambient light, so that it interacts with the object and the data is being picked up by the eye, and we try to see whether we can see something inside. So this is basically, we are trying to actually look at the property of this black box by some external measurements using some external probes or energy, right? So this is one way. Second thing is we can shake it. So we are basically trying to pick up the sound. In fact, have a feeling of weight. So if it is very heavy, we can say it can be something very heavy object, or some dust we can have, right? So depending, or even at some point we can even smell it and see whether it's actually something having some fragrance or something, right? So what basically we do is we are actually utilizing the sensors, which are basically the measurement devices in our body, and trying to see what is inside with the help of external sources like light, or by shaking we are generating sound, right? So that's the idea. Now with this one, this is exactly what I was telling in the earlier case, where there is a probing wave which interacts with the object and then we try to measure it. So this particular slide, I just want to motivate you, saying that we actually do it in our daily life. This is nothing like a different, this concept is not completely foreign to us. We actually do it. So I want to motivate this concept in real life. We will do a quick survey of what all things that we can relate to these concepts. So let's have a little bit more on this abstract, approach to this problem, and we'll go for those examples. So again, I'm repeating, you have got a probing wave which interacts with the object, and the interacted data is being picked up by some detectors, and that is being utilized for generating the image of the object. Now we can divide this into three problems. So here comes the first step in an abstract viewpoint. So we are going to divide this problem into three. One is what is called the forward model or the forward problem. So what does it tell you? It tells you that how this probing wave interacts with the object. This is what the forward model is. So suppose it is a light, it tells you how light is going to get affected by the object, or whether it's going to get reflect, or it's going to get refract, is it going to get scatter, we don't know. So those things we have to model it and tell how light is going to behave inside the object. So this is governed by a set of equations, and you will see that is basically it's a wave equations, or partial differential equations, or to be specific, basically wave equations, right? So that's something which we will see. So it tells you that given the object and the object property, and given the which type of probing wave you are using, you want to find out what is the distribution of the probing wave inside the object. So basically, it involves solving a partial differential equation, and you have to find out what is the solution, right? And we are interested in the solution at the boundary, because you cannot put a detector inside the object. That is destructive testing. So usually for the imaging problems, you have to put the object at the boundary, right? We cannot take measurement from inside human brain, right? It's difficult. There are invasive procedures, but usually we want to avoid that. So measurements are always at the boundary, right? So the forward model will give you what is the distribution of the probing wave inside the object by solving some appropriate equations. Whereas measurement model will give you what is the value of that particular interacted wave at the boundary, or the solution of the partial differential equation at the boundary, right? And then inverse model is completely different from these two. Inverse model will tell you, okay, given the probing wave and given the measurement at the boundary, you have to find out what is the object property. That is the inverse model, right? Or the imaging problem, inverse model and inverse problem, or the imaging problem. So the idea is that now we don't have the object property at your disposal, but you know what is the probing wave, and you know the measurement, and of course you know what is the forward model, but you don't know the object property. This object property will always be coming as a coefficient of the forward model. So we will come to these points with explicit examples. So in that sense, basically this can be considered as a coefficient recovery problem, which we will see, right? So these are the three concepts based on which we can actually view all these imaging modalities: the forward model, the measurement model, and the inverse model. So this is where a lot of mathematicians have actually contributed to the field of medical imaging. So this is something you can keep in mind. So let's have relate this concept to real life examples. So as I written here, my intention is not to actually solve this problem or show you the solutions or nothing like that. Even this problem is relevant, or is this problem properly formulated? I'm not worried about it. These are just some random questions. You can think about it. So you can see that when the ducks moves in a pond, it actually leaves behind a wave pattern, right? So the questions that you can ask is, given a trail, water trail, like some water pattern, can you actually identify the duck? Or this pattern, is it unique to a given duck, right? So just think about it. So similarly, you can see a unique or aroma associated with each food. So I'm sure that by sensing the aroma, you can actually identify the food, right? Can you see an inverse problem and a forward problem in this particular scenario? Just think about it. Similarly, you can see this thing. I'm in Mumbai, and this is quite common here. This manholes in the roads, where it's a drainage. Basically, the water actually goes inside, and during monsoon you won't be able to see it, and especially in the dark. But still, you can identify it from how. So by visually you can see the turbulence, or if there is no enough light, you can actually see hear the sound variation, right? From there we can actually sense, okay, something is there. So can you identify this as an inverse problem? So similarly, the bats, this echolocation is actually very quite obvious. So bat, they say it actually generates an ultrasound. This ultrasound will actually interact with the nearby objects and get reflex. The bat will sense it, and it can actually find out the distance, the shape, and the location. It's amazing, and some people have actually worked out how to quantify these things, right? So this is a very classical case of inverse problems. You can have a look at it. This learning process in children. This is really interesting for me, at least. So I have seen that if you look at this less than 1 year old kid, you show some objects to them, and in front of them itself you actually hide it under the pillow in front of them, so that they can actually see that you are actually hiding under the pillow. But then at this age, he or she won't be able to identify that, understand that we have actually hidden the object. It takes some time for them to understand that that object is actually under the pillow. So this is basically a learning process. So I just choose this example because we are basically, there is a hidden object and we want to find it, and all the senses, everything is well developed for the kid. It can see it, it can have touch sensation, it can hear, but still it won't be able to do it, probably because there is a fourth thing that is required for imaging, the post processing, and the brain is not developed that time. So it takes some time, and that's a learning process, right? So these things you can actually, the learning process of kids, can you categorize it as an inverse problem? So just think about it. Similarly, this ragas, right? The musicians make different film music based on raga. Now, there are people who can actually identify the basic raga from the given film music. So, is it an inverse problem, or can you catch the sometimes when you hear some music, you may think, okay, this is very familiar, or have heard it somewhere else. So, can you catch the copycats, and is that process an inverse problem? Now, this is something which you all should look at. Do a Google search. This is something very relevant to you. This is one of the classic papers in inverse problems. So the question is, by measuring the eigenvalues or the fundamental frequency and its overtones, can you actually find out the shape of a drum? So when you use a drum, the sound waves will come, and there are eigenvalues associated with that. From that eigenvalues, can you actually find the shape of the drum? Or if you put it a little bit more abstract, can you identify the domain from the eigenvalues being generated, right, for a particular a particular operator, right? So this is something which you can actually look at, something in your domain. So go and find out this. Can one hear the shape of a drum by Mark Cack? I think it was posted in 66 and it's solved in 90s. A very classic paper. I think you should all look for this particular thing. So it's a very important problem in inverse domain. Now, deblurring. So you might have observed that the visual in a very misty day is being it's not very clear, right? So what is happening? So at the background you can actually see the real one, but then the light being reflected from those buildings are scattered because of the mist, and you are getting some measurement. Now the question is, can you actually deblur it? So the blurring has happened because of the mist. Can you deblur it? And you can see that this is basically based on what are called the integral transforms. It's basically it's a convolution which is happening here. A particular noisy data is being convolved with your actual image, and that is being so that your actual image being smoothened out, and that's what being measured. So basically we this problem can be cited as a deconvolution problem most often. So you think about this one. Similarly, there's another problem is, for example, something related to this. You might have seen in lakes when the sun reflects, and when a wind blows, you can see the image in the lake actually blurs. So from the blurring, from the blurred image, can you quantify the wave velocity? Wind velocity. Again, think about this as an inverse problem. This is a very classical example, pulse oximeter. Nowadays, it's very quite common in this COVID area, time. So it uses actually near infrared light. So the light source is being forced to. We illuminate the fingertip using the near infrared light, and the data is being measured using some optical detectors, and then it is being converted to what is called the oxygen saturation. How it is done, I will explain later, but this is a very classical example of inverse problem. So here the light is near infrared light is a source, subject is human body with especially in the site of human finger, right? And the measurement detector is an optical detector. So it's a classic inverse problem. So what is the coefficient recovery here? Here the blood oxygen saturation, which is a property of the blood, right? How much oxygen content the blood has, that is being find out, right? The forward model I will explain after a few slides. So this is a very classical example. And then you have dental images. This is X-ray imaging, basically how X-rays interacts with the object. So the X-ray is getting absorbed by the teeth, and the contrast is formed in the film, right? So this is basically projection. The data is being projected. A three-dimensional object is being projected to one dimension, right? Sorry, two dimension, right? And if you go for a tomography, you can actually create a three-dimensional picture of the tooth. That is done in cone beam computed tomography. So this is again an example of inverse problems. This is a really interesting example, which is this near infrared spectroscopy for art. So you can see in olden days, people used to paint and they do a lot of corrections, and the corrections are being done one over the other. So the question is, can you find out all those corrections layer by layer? So you cannot distract and find out. So basically you can do a spectroscopy to find out and reconstruct each and every layer. So basically we put a light, the light will interact with this material and it will give you the depth information, and that can be made into a tomography or that it can be made into images at different depths, right? So this is again a class of inverse problems which has got an application in arts. Police dogs, I don't have to say, you just you know it. So it sniffs, and there is a learning process which is the training days of the dog, and then at some point when it is taken to a crime scene, it detects, and they'll try to from its learning process, he knows how to detect it. So I'm not going to elaborate this. Right, so basically it tells you that there is a probing wave, it interacts with the material subject, and then there is a measurement, and then you have to find out what is the object property. That is the inverse problem, right? So it's not very easy. You have to have, you can ask several questions, which is outlined here, like what a wavelength I should use, which energy, should I use ultrasound, should I use light, X-ray, gamma ray, which one I should use in the electromagnetic spectrum, should it be uniform or focused, which wavelength I should use, should I use a laser or a normal light? So there are so many questions we can ask. I'm not going to these details, which may not be very interesting to you, but let's, I just want to tell you that there are so many things that you have to think about before making an imaging system. And this is very interesting thing. So you can see I have put a laser source to a rat brain, and the data is being collected by a camera, and you can see on the lower part of this picture, there are some noise. This is, you might have seen this in all television sets, this pepper noise, right? But the moment you calculate what is called the spectral contrast, which is nothing but the standard deviation, the ratio of standard deviation to the mean, which is being calculated in the small window, you can see it actually reveals a lot of blood vessels, right? So this is basically a very simple image processing which can reveal some data, and otherwise it looks like a noise. So I just want to give you an idea what we mean by post processing. This is something done in the computer. We cannot do it in our head. So this requires some computation. So we will now see. We will try to motivate this forward model first, and then we will go to inverse problem. So I think I have to go quickly. So let's look at some experiments to motivate you. So let's have two beakers here. So I just want to pause here. So are you following me? So am I going fast?
No, sir.
So any questions so far? Okay, so shall I continue?
Yes, sir.
Okay, fine. So if you look at two beakers I have kept here, and there is a rod, black rod I have inserted. Now, forget the upper part. I'm looking from the lower part, and I want to see whether I can identify this rod. You can see if the beaker contains water, I can actually see it. How? Because the ambient light interacts with the object and it falls on my eye, and I can easily detect. But at the same time, on the left side, you cannot, because still there is an ambient light, but the light is being scattered and you cannot see it. So there is scattering and absorption even happening. So we will see these two processes to motivate you to certain forward models. So let's have a look. Let's look at a beaker with some small droplets of milk added, so that there is slight scattering. And you put a laser from one side. You can see that the laser will travel almost in a straight line because it is not scattering. Scattering means it will change the direction so that you can see from everywhere. You will see another picture, right? At the moment I put some ink to this beaker, you can see that the light will not reach from the right to the left, but it is being absorbed in between, in the middle. By the time it reaches the half of the beaker, it is being absorbed. So there is an absorption happening, right? Now you can see that there is absorption and scattering happening. That means the light is not in a straight line, it actually spreads a little bit, and it is not reaching to the left because both absorption and scattering has happened. Now, you can see that this particular thing can be utilized to find out some inhomogeneity, some hidden object put inside. So you remember I told you some hidden object in a black box. So you can consider it like that. And you can see that this external light source can be utilized to see an hidden object. But unfortunately, the hidden objects in actual tissue, it can be a tumor, it can be cancerous part, right? So these particular things are surrounded by tissue, which is actually a highly scattering material, right? So of course it depends on which probing way we use, but most often it's a very highly scattering. That's why I put an absorption and scattering here. And you can see that the light is being scattered and absorbed by the surrounding tissue, so that we cannot guarantee it's going to interact with the tumor or the cancer. Even if it interacts, it's very difficult to sense it. So I just want to show that here. So you can see if the scattering and absorption is much less, then it will be obstructed by the object, and you can see some light coming to the left from the right side, right? And from this measurement, I have put a camera here. From this measurement, can you actually identify this obstruction? That's a question. And you can see that in real life, when the water flows and when a stone blocks it, the water wavefront will get distorted. So can you identify from the wavefront measurements, can you identify the shape of the stone, right? So same old story what I told you. Now, how do you do that? So one way to do is, you have to take a measurement without this object if possible. And then you compare it with the measurement that you are getting with the object. Surely the difference will be large, and use some inverse model to find out what is the object. This is the essential idea of imaging. So you have got two measurements, one with the object and one without the object. You take the difference and develop an inverse model with which we can actually reconstruct this object. This we will see how to do that. So as I told you again, forward measurement and inverse algorithm. So I'm going to skip it. You know it, I guess. So let's go to the case where, as I told you earlier, the light can get absorbed, light can get scattered, and it can actually undergo both. But now we are going to do some forward model in the case where the light, in fact, to be specific, it's X-ray, which is going to be in a straight line. So the idea is that now I have got an X-ray or a light in a medium such that it is going in a straight line. But the idea is that it is an absorbing medium, so that the intensity of those rays are being decayed along that line. So what do you expect as a forward model? So the idea is that there is a light which is going to be in a straight line in a medium, but along the line, the absorption, because of the absorption of the medium, the light intensity or the X-ray intensity is going to decay. So that's a scenario. So how do you model it? So the idea is that, as you know, this is everything is happening in a straight line. So we don't need a partial differential equations. The variation is along the line. So you can do a ordinary differential equation is enough here. And you can see the statement that the fractional change in the intensity is in fact proportional to what? The distance and also to the local absorption coefficient. So that statement is given here. You can see this statement. So this is actually what is called the Beer-Lambert's law. And if you put it under the limit that delta Z tends to 0, you can have a first order differential equation. And the solution to this is nothing but an exponential decay. So this is the Beer-Lambert's law. So the idea is that for the simplest case where the probing wave interacts with the tissue such a way that it do not scatter, but it just move in a straight line, and it get absorbed along the line, but it never scatter. The best example is X-ray computed tomography. In this case, the mathematical model or the forward model is Beer-Lambert's law, which is nothing but a simple first order differential equation. And the solution, you know, is like this. So here the assumption is mu is constant. So what happens if mu is not constant? Basically, you have to do an integral, and you can see this one. This is the case. When so it's continuously varying, the input and the output intensity is related to e raised to minus integral mu of x dx. Right? So here the assumption is the line is along the x-axis. That's why I put mu of x dx. But it's in an arbitrary line, you have to basically take integral mu of s ds, where ds is an element along the line for a given line L. Right? So it's an integral along a line. Right? So this is the simplest forward model that you can think about. And we define what is called a projection data, p theta of t, as the ratio of the input to the output intensity and the logarithm, so that we can remove this exponential. Now you can see it's a mu of x dx. Now you can see that if you are using the first relation as shown here, then you can see that the relation connecting I0 to mu is nonlinear. So what is our aim? The aim is, given I0, given this forward model, and given I0 measurement, I want to find out mu, where mu is the absorption coefficient. That is the inverse problem associated with this. And you can see if I use this exponential model, you can see that I0 is related to mu in a nonlinear fashion. But luckily, this nonlinear inverse problem can be linearized easily by defining a measurement which is p theta of t, so that now p theta of t is equal to integral mu of x dx, which is a linear, because integral operation is linear, so that you have got a linear relation between the measurement and the mu. So my aim is to find, given p theta of t, you find mu. Now you are surprised what is theta and t, that we will see here. So you can see that, suppose I have a scenario where there are two tanks with mu1 and mu2 being the absorption coefficient. Now I want to find out mu1 and mu2, but I have got only one X-ray going through it. Can you do that? It's not possible, because you have got two unknowns and one measurement, as shown here in the first block. So in this case, you have to generate one more data. So how do you do that? The easiest way is to you cannot just change intensity to generate one more equation, because if you change IO will also change, so the left hand side will be the same. So you are not going to, it will generate the redundant relations, right? So that's not going to help you. So basically you have to change the angle. So we have to put a line which is inclined at an angle theta. So that will generate a different distance and the different set of equations as given in the last talk. L1 dash mu1 plus L2 dash mu2 is equal to p1 dash. Now mu1 and mu2 remains the same in the chamber, but the distance the X-ray has to travel is L1 dash and L2 dash, which is not equal to L1 and L2, so that these two equations are different. So you have got two equations and two unknowns, you can actually invert it, right? So that's why in computer tomography, the data is taken in different angles. So put it together, you can see that this is the case for the X-ray tomography. You have got a region of interest to be find out. So what you're going to do is to have projection data at different angles and also at a different regions. So for example, this is my region of interest, and you can see that this particular ray is going through this region, but the next ray, which is IO double dash, is not going through this region. So if I am going to use only one ray, even if it is at an angle theta, I may not be able to reconstruct the region of interest, because it has to travel through the region of interest. Region of interest means something that you have to recover, like a cancer or a tumor like that, right? So in order to solve this problem, what they do is they will put several parallel rays. So you cannot have just one ray, you can several parallel rays at several angles. Now each parallel ray is measured using what is called the T, and each angle will tell you what is orientation. So that is being depicted here. So you can see the T is nothing but the distance from the origin to that particular ray, and angle is the angle between this particular perpendicular to that ray with respect to the x-axis. So this is what is called the p theta of t. Now the funny thing is, this integral L mu of s ds, which I told you, is nothing but, if you look at this object, it has got an absorption coefficient. Now this is being integrated along this line. You can see this is this particular absorption coefficient is integrated along this line, and you can see that this is nothing but what is called the Radon transform. So Radon was a mathematician who invented it, like maybe, I don't know, in early 90s. 900s, 1900. So those time he has developed this Radon transforms, which tells you that if you have a function, then you look at all the line in area of this function under different lines. So you draw as many lines as you can at different orientations, and you find out the area of the function under these lines, and that is actually transform this function to a new function, which is the Radon transform, right? So this is basically the Radon transform. So integral L mu of s ds is nothing but the Radon transform, and this is actually the properties of the Radon transform have been well studied. You can have a look at what is book by Natterer. So this will give you a general idea about how to view this problem, X-ray computer tomography, from the mathematical viewpoint. So here the forward model is Beer-Lambert's law. Measurement is the projection data, which is nothing but the Radon transform, and inverse problem is how to find mu given forward model and the measurement. So that's the idea. Now, there is a strong theorem for it. I'm not going to explain all this stuff, but then you can see that there what is called the Fourier slice theorem. So what does it tells you is, in this example, if you look at this projection data, what does it tells you is, you take the Fourier transform of the projection data, and you can see that this Fourier transform of the projection data is equal to the Fourier transform of the function mu constrained to a line at the same inclination, but in the Fourier domain, in the UV plane. So basically, when you have measurements at different angles, basically what you are doing is to get the data in the UV plane. So this UV plane is the Fourier domain of the object function mu, which we want to recover. And by measuring the projection data and then taking the Fourier transform, we are basically getting the data along these radial lines. Now what you have to do is to interpolate this to a rectangular grid and then do an inverse Fourier transform that will give me my mu. So this is how they reconstruct, and these are some reconstructions. This is the original one, and this is the reconstructed one using this method. So Fourier slice theorem is nothing but the rotation theorem in two-dimensional Fourier transform. So you can have a look at that. Now there are another. So I'll just skip this. There is another way to do this, which is called simple back projection. So the idea is that you do a projection, which is so if you look at this particular object, you can see that if you illuminate it, you can see some shadow here, and you back project it so that you can see in this figure you are back projecting it so that you will get a strip here, and you do it for every possible angles, and you can see something being reconstructed at the center. So this is just one slice, 2D slice of a three-dimensional object. And if you do it for every slice, you can actually reconstruct this object. So basically what you do is, whatever data you are getting, you smear it back to the object domain, and then you do it for all angles and keep on adding it. So that process is actually being utilized here, and you can see that so this particular integral will tell you how to smear it back. So this is a delta function, so it tells you that you have to confine this to those x and y such that x cos theta plus y sin theta equal to t. So all this data is being smeared back along this line, and do it for every t at a given theta, and then add along all theta. So this is called back projection. Now this back projection will never be equal to the actual projection, and you can see that basically the back projected image is actually a convolution of the original image with 1 by r. And this has something to do with what are called Hilbert transforms. So if you write it in convolution and invoke the Hilbert transform, which is nothing but, what is Hilbert transform of a function? Which is nothing but the convolution of the function f of t with 1 by t, right? So you can see that these things are related to the Hilbert transforms, where you may be interested in looking at. And then you can do a filtered back projection. So you know that this particular image is spoiled by a convolution with a function 1 by r. So in the frequency domain, it is 1 by mod omega or omega, depending on how do you take the integral limits. And then I can do a filter by multiplying it with mod omega to remove this function. That is being done in the filtered back projection. You can see that it actually generate nice images. So left side, these two are actually original, and the right two of them are actually the reconstructed. So these are the things done in X-ray CT. Now let's look at the diffraction tomography. Now I told you that the X-ray is being going in a straight line, so we need only differential equations. But what happens when it encounters scattering? So as I told you, now the intensity is distributed along X, Y, Z. It is not going in a straight line as in case of X-ray. So you have to look at partial differential equations, and the equations that comes in case of a light is actually what are called Maxwell's equations on the left side of this block. And you can actually, these are basically some set of equations in electric and magnetic field, and then it can be converted to wave equation, which you are familiar, I'm sure. And this wave equation can be, by removing the time factor, you can actually convert it into what is called the Helmholtz equation, right? So you do the method of separation, and then you can see that you can convert it into del square E plus k square rho square E is equal to 0, which is nothing but the Helmholtz equation. It's an elliptic partial differential equation. And what is the problem associated with this? So the forward model is, given this equation and given the refractive index, now the property is refractive index of the material, you have to basically find out how these waves are actually going to get distorted by the object. So you know that for the Helmholtz equation, there are several solutions. One is plane wave, which is of the form e raised to I k dot r. And then another equation solution is the spherical waves, right? E raised to I k r by r form, right? Now, if it is a plane wave, this plane wave is being distorted by this material, and you can see the distorted wave here. So how this distortion happens is a forward model. For that matter, you need the n, and n actually comes with k. So you can see k is 2 pi by lambda n. So it's a coefficient. So the object property sits in the coefficient. E0 is the distribution of the probing wave, and that is being distorted here, right? So this is how you have to view. So this is a forward model, and it's basically a Helmholtz equation, and you want to solve this Helmholtz equation. That will tell you how this plane wave interacts with the object. Now, what is the inverse model? Inverse model is, given the measurement, given this distorted wave, and given this Helmholtz equation as a forward model, and the input, which we already know, can you find n of r? That is the inverse model, and that has to be done. That is the idea of diffraction. So you can see, when I moved from computer tomography, which uses X-rays, to diffraction tomography, which uses light, which is a different imaging modality, you can see the questions that you can ask is the same: forward model, measurement, and inverse problem. So there are common things with which we can approach as a mathematician. Now, again, you can invoke the Fourier slice theorem here. Here, instead of radial lines, you will get it in semicircles. So you can have a look at Kakan-Slaney book, which is open source. You can just download and look at it. Look at this notes. Basically, it's again the invoking what is called you can prove all this stuff using what is called the special functions approach to solving these problems using Hankel functions and all. Right now, this is something which I would like to stress. Let me see if I have time. So, what am I running out of time? Hello.
No, sir. It's okay, sir.
Okay, so let me see. Okay, so this is something which I would like to tell you. So I always told that we can actually do what is a imaging problem, right? So how to do that? I will give a glimpse of how to do this. So you can see that. Suppose the wave is traveling in a free space, then you can see the forward model is Helmholtz equation, but the coefficient is corresponds to the free space. That means there is no object; it is in a free air or in a vacuum. That is k0, and the corresponding field is u0. Now, the moment there is an object, you can see that this equation will get perturbed to del square plus k0 square us is equal to minus u into o. Here, us is a scattered because there is an object. So the plane wave is traveling in free space, and then I'm going to insert something in its path. Like I can show it here. So the plane wave is going in a free space. So suddenly I inserted some object here like this, and then you can see the plane wave will get distorted because of this presence. So in that case, the light is being scattered, and that component is us, and you can see del square plus k0 square us is equal to minus u into o. So here the idea is that O represents the object. Now this is, and I want to find out what is US. So we again invoke the concept of what delta Green's functions, right? So so you replace your right hand side with a delta function, which is given here, and then the solution is the Green's function, and then the solution to US with the forcing function u into O is nothing but the convolution of the Green's function with the object function. Right, so this is the concept, but the problem is on the left side you have a scattering coefficient, and the right side you have a u, but u is nothing but u0 plus us. It's a total field. So you have to do some linearization, and then you can see that basically this is the linearized version where you can find out the scattering field from the incident field and the Green's function, and this is the basics of most of these imaging modalities to do image reconstruction. Right. So in order to see why there is a need of linearization is the inverse problem here is nonlinear, because what we so if you look at this previous slide, you can see that in this equation we want to find out refractive index, but refractive index is a function of k, but k is being multiplied with e0, and what is my measurement? E0 at the boundary. So the quantity to be recovered is multiplied with the function, which is my measurement. So this product actually creates a nonlinearity, and that has to be removed, and that is being done here, and this is called Born approximation. So basically this procedure is nothing but you invoke the idea of Green's function. You do a perturbation model. That means the object is going to perturb your equation. You write it down that in that way, and then invoke the idea of Green's function, convolve this in Green's functions with your object function, and then do a linearization. That will give me the solution to the imaging problem. Now the idea is that US is given to you because this is my measurement left hand side. Green's function is known to you, and incident field is also known to you. You want to find out O. So this is basically an integral equation. So this is basically a Fredholm integral equation of first kind. You can actually do an inversion, or you discretize it into making the form of Ax equal to B, where B is my mu s, A contains G and U0, and X is my unknown, which is O, right? So so basically most of these problems will finally reduce to what is called the integral transforms. So if you, so I'm not going to show those details. So I just want to stress this fact once again. So if you look at the first one, X-ray computed tomography, the forward model is nothing but the first order ordinary differential equations, and the solution is very simple exponential. Fine. But if you move to the case where the light actually scatters, then you cannot use ordinary differential equations. You have to go for wave equations or the corresponding Helmholtz equations. So wave equations, you take the Fourier transform of this, and you will get this one, right? That's all. So you can actually get this particular format of which is a Helmholtz equation, and then you can see that even for ultrasound, even though it is completely different from electromagnetic wave, this will also give me wave equation type models, right? So that even if it is an ultrasound, we can still work with the Helmholtz type equation. So the complexity has increased. Now the problem is not solved yet. So the idea is that if you use a light in human body, even the wave equation is not valid. The wave equation will not be suitable for, it is valid, but it is not suitable because it's very difficult to solve. The reason is tissue contains a lot of scatterers. So in this case, we have to come up with something new, and that has been done like, I don't know, 60, 70 years ago by Professor Chandrasekhar, and that is what is called the radiative transfer equation that is being shown here. So here, instead of looking at the wave picture of the light, we look at the photon picture. I'm sure that you guys have learned something in your minor BSc physics courses. That means it has got dual role, right? Light has got dual nature. One is light, a wave, and the other is photon. So if you have to invoke the photon picture, and you can see, you can write an energy balance equation of this form. So it tells you that the rate of change of the flux at some point is equal to things which add energy to it and things which remove it. So you can see the things which add energy is the source and scattering from different directions, and things which take it away is the divergence and also the absorption. So that way you can view this particular equation. And this is an integral differential equation, and it's very difficult to solve. So what people do is to reduce it to what is called diffusion approximation. And the funny thing is, as I told you, you cannot use Helmholtz type of equations in real tissue. Why? Because it is not going to, it is not the way. It actually scatters a lot that the K sitting here is too high to be solved in all practical cases, so that we cannot use it. But at the same time, if you want to reduce this particular radiative transfer equation to a diffusion approximation, we are still using the Helmholtz equation, because you can see this radiative transfer equation contains several variables like r, s cap, t. What is r? Spatial position vector. S cap is the angular coordinates. This is spherical coordinates. It is nothing but theta and phi, right? Or unit vector, cos theta, sin phi, sin theta, sin phi, cos theta, right? So that particular unit vector, and t is the time. Now, in order to reduce this equation to diffusion equation, you can see this s cap vanish. So how do you do that? Basically, what you do is you fix a position vector and you look at a sphere around it. Now you know that if you solve Helmholtz equation in a sphere, the solution can be decoupled into r and theta and phi. The function which actually represents theta and phi are called spherical harmonics. So this is exactly like a Fourier basis. So the spherical harmonics can be utilized to expand functions under appropriate conditions, like what you do with the Fourier expansions, right? So if you do that and then invoke the orthonormal property, you can actually remove the angular component, and you can actually get diffusion approximation. So you're basically removing x cap from this. You have got only t. In fact, a t can also be incorporated. I haven't shown here. You can incorporate r and t, and you can remove s cap. That is called diffusion. So I'm just giving a glimpse. It's very difficult to tell everything here. And similarly, for photoacoustic imaging, you can extend this wave equations, and you can see most of these are partial differential equations with several additional terms. right? So this is how the forward model changes. And what are inverse problems associated with this? Recover in the coefficients. So that's how it works. So I'm just skipping the MRI. I mean, I don't have time. So let me see if I can show something. So again, coming back to this forward model and inverse problems, I'm just showing the same things here. So I'll just tell this once again. So yeah, so let me tell this. So here again, as I told you, what is called the diffuse optical tomography. So the forward model is nothing but how the light interacts with the tissue. And as I told you just now, I finished what is called diffusion equation, which looks like this. And what is my aim? My aim is to find phi given the measurement at the boundary. So sorry, forward model is to solve for phi given the tissue property. What are tissue properties? Mu A and mu S dash, which is the absorption and scattering coefficient. Now, what is the inverse problem? I want to find, given phi at the boundary, I want to find mu A and mu S dash. That is the inverse problem. Right now, there are other possibilities and some theoretical questions that as mathematicians can ask, what are called well-posedness or ill-posedness. So this is being defined by Hadamard. So the idea is that if you have a equation of this form, say for example, this one, forward problem, you can see there are three questions I can ask. What is that? One is whether a solution exists. Yeah, that is answered because most of these things are being developed from physical phenomenon. So the physical phenomenon represents the existence of solutions. So that is being always answered. Second is the uniqueness. So is there any unique solution? So is there any two solutions or can be? So I don't have to explain. So the existence of a unique solution is the first thing. Second thing is, so you have to basically solve it for a given initial condition or a boundary condition, right? Now the question is whether that solution will have a continuous dependence on the initial data. That is a stability problem. So the continuous dependence of the existence of a unique solution and the continuous dependence of that solution on the initial data. These are the three conditions for well-posedness. And if that is being satisfied, this problem is called well-posed. Now, forward problems are in most cases is well-posed, but the inverse problems are not. One of the reason is if you can see that the measurements that we always have acts as the initial data here, and the solution is nothing but the coefficient. So we are actually looking at the continuity of the coefficient with respect to the initial data, which is my measurement at the boundary. And you can see that the measurements at the boundary are always partial. You are not going to get from everywhere. Most often it is in discrete areas, not continuous. And third thing is mostly it is corrupted with noise. So in all practical cases, inverse problems are ill-posed, but there are still, you can ask many theoretical questions on ill-posedness of an inverse problem. So it's completely pure mathematical viewpoint. So basically you have to work with what are called Hilbert spaces, or in some cases using what is called Sobolev spaces, right, with the help of distribution theory. So these are the space settings where you can actually work and try to solve this type of questions. So this is being told here. So inverse problems are often ill-posed, and discrete sense it means it's ill-conditioned. So the associated metrics will be what is called, it's a completely condition number will be very large so that you cannot invert it, and we have to go for what is called the regularization. So regularization, I'll tell you some idea about that. So coming back to our problem, so this is basically the perturbation approach. So you have got the measurement, and I'm going to perturb it because my absorption coefficient. So I am going to perturb my absorption coefficient here because I want to find out my absorption coefficient. So when the absorption coefficient perturbed by an amount mu del, my phi will perturb by phi del, which is my light flux. And then I can write something in terms of phi del. And you can see this now comes in the form of a perturbed equation, and you invoke the Green's function. Remove this right hand side and put a delta source, and then you can see you can write down phi del in terms of the Green's function, the total field, and the perturbed value, right? And now phi contains phi del, so you can remove and put phi 0 here, and that process is called a linearization. So this is essentially what we do in imaging, and you can see that phi del is equal to -3 mu s dash g 2 Green's functions and then mu a del. And my aim is to actually do some in the computer so that I can discretize it. The left hand side is my measurement restricted to boundary. The right hand side has got a matrix represented by 2 Green's functions, and mu del is my unknown. So you can pose it as Ax equal to B. And as I told you, because of the ill-conditioned problem associated with this inverse problem, A has a high condition number. So the problem is we have to basically regularize it and then try to solve this. This is a rectangular matrix because the number of measurements is always be less than the number of unknowns. Meadal is distributed everywhere in the tissue, but the measurement is restricted to boundary. So the number of unknowns will always be greater than number of measurements. So A is always a rectangular matrix. So you have to go for a pseudo inverse. The best way is to go for a least square minimization, and that is being shown here. So X minus B, you had to solve this particular function and with a proper regularization parameter, where lambda is a regularization parameter, and this is what is called the Tikhonov regularization. Right, so then you can see that using finite element method, you can actually do some 3D reconstruction of the object, right? And this is a place where you can actually contribute. So if somebody is interested in finite element method, there are so many mathematicians working in this field. Basically, it's an application of what you call the Sobolev spaces in real, real problem. So you can have a look at all these stuffs in this. But anyway, you need to have some computational skills for this purpose, or you have to develop, right? So I think I should. I think I will just go quickly to one of the problems that we actually did. Or maybe I think I should stop now the time is over, so I don't think that I have time to do it. So I think I am stopping it, so you can have some questions.
Sir, there are a few questions in the chat box, sir.
Okay. 1 minute.
Should I read it, sir? Or?
No, I can read it. That's okay.
Okay, sir. Okay.
1 minute. 1 minute.
Okay, sir.
Okay, the first question is, as a BSc mathematics student, how can I reach to this field? What course do I need to take? Okay, so BSc Maths, say for example, I have survived with the basics of linear algebra and basic real analysis and functional analysis and PD theory. If these three courses, if you do very well, I think that is enough for a basic understanding of this field. With respect to what I'm talking is with respect to my experience. What you can do is to get a master's degree from some colleges, like MSc Maths from some IITs, and try to talk with people in other departments and see whether you can do some combined work with them. And it need not be always be in imaging. It can be in different fields. So, for example, in our institute, there is something called systems and control. So basically, they are working in control theory. Most of them are really good at math, although they are engineers. They are working in PD and OD control, and most of the students actually do a lot of courses from Maths department as a part of their PhD. So that way, you can actually try to get into some MSc programs in IITs, and then try to interact with the people from other departments and see whether which particular problem you will be suitable. That approach is better. Second, sir, could I have the PPT of yours? I need to study them a bit deeper to understand them deeply. I will think about it, because sharing PPTs I have to think. But I can definitely give you some references. So can we reduce the harmness to the living cells by some waves of source during scanning by the application of mathematics? I mean, that's actually a good question. I mean, the why people started, see, X-rays actually works well. X-rays are in the clinics, in the hospitals. People use X-rays a lot. But why did you, if X-ray is working fine, why people want to use light for this application? So, for example, there are so many people, including myself, spending the whole career in trying to see whether the light can be utilized for imaging purpose. But if X-rays is working fine, why do you need it? The answer is X-rays are harmful to the living cells, as he pointed out. So you cannot use it for many overexposures, right? There are some limitations of taking X-ray images, right? So that's why people started to see whether we can use light which is not harmful to the living tissue, and that's why we started using light. But in contrary to what you said, like whether mathematics is going to help. Actually, the mathematics is not helping. It is actually causing problem to the light, because the moment the light comes to the tissue, it actually scatters. And when it scatters, you have to invoke the PDEs, and you have to look at the coefficient recovery of a PDE, which is much, much more complicated than what we do with ODEs in X-ray CT. So the life is a bit difficult. So there is always a trade-off. The safety is okay with the light, but at the same time, the mathematical equations involved are a bit complicated, so that the imaging is difficult. So that's how you have to see that. Second is feedback form. I don't know what is that. Okay, that's all. Okay,
One more question is there in the chat box.
is it possible to diagnose all type of tumors? What are the exceptions? See, the idea is that it depends on what where it is, and how. I mean, see, for example, if it is MRI, basically it looks for structural changes. But if you use a light, actually it can look at the blood vessels in the tumor, and where it is located and how small or big it is, it differs. So depending on different types of wavelength that we have and how deep it is, the things can be difficult. So, for example, if I have a deeply, if I want to image a deeply rooted tumor in the human brain, with that current technology and know-how that we have, it's very difficult, because the light has to go inside, it has to interact with the deeply sitting tumor, and it has to come back and then have to do. So light is scattering, it is getting absorbed. So the technology that we have right now is not enough to get a very good images. So it depends on what type of tumor, where it is sitting, how big it is. All those things matter, and then you have to appropriately choose an imaging modality. Yeah, that's all right. Hello?
Yes, sir. Yes, sir. Thank you, sir.
Fine.
So on behalf of all the participants, I would like to express the sincere gratitude, sir.
Yeah.
And
sure.
Arya, now you can have.
Okay, sir, the class was very interesting. You just showed that there are many opportunities for us, or we can use maths in many variety fields. Now, I welcome Miss Akida, Assistant Professor of Vimala College, Thrissur, for vote of thanks. Akida, Miss.
I think she has some network issues. Swarna, miss. Akita?
Yes, Miss.
Yeah, you can say.
Yeah.
Good evening, everyone. It's my privilege to have been asked to do education. I extend a big thanks to Dr. Hari Verma, Assistant Professor, IIT Bombay, for this valuable section. I also thank our Principal, Dr. Sister Beena Jose, and Dr. Sister Sylvie Matthew, DBT Star College Coordinator, in their absence. I also thank Dr. Anjali Kishore, Coordinator of this webinar, and Ms. Sorna KL, Head of the Department of Mathematics. I'm thankful to all the participants for attending this session. Thank you all.
Thank you.
Thank you, sir, once again.
Yeah, sure.
And
So,
thank you.
yeah, please.
Yes, sir. Sir, you can say.
No. So, so I hope the attendees got some idea about the problem.
Yes, sir.
It's a bit difficult to find the balance between, because the audience is different. I mean, I cannot just say just the mathematics, because then they won't get an idea what is actually going on, right? So what I want to suggest to all of you is to explore. I mean, now you can just Google and find out the whole profile. Everything is visible.
Yes,
So
sir.
I just want to say, just search inverse problems with the medical imaging keyword. They'll be able to explore so many resource persons, even in India and abroad. I mean, of course, So I hope that message I have conveyed to the students. I mean, that's the only thing I can do within this limited time.
Yeah,
Yes, sir. Very
definitely,
much,
sir.
sir. Thank you, sir.
Yeah. So anyone who wants to know more about it, you can write to me. I can help you, and I can also accommodate interns if they want during
Very well. Thank you,
summer and all.
sir.
But of course, I mean, I cannot pay them. Basically, it's internship.
It's okay, sir. No problem, sir.
But
Very congratulations.
some guidance I can give, or you can approach Professor Nandakumaran as well. So we collaborate and do. So if somebody wants to work with Nandakumaran and me, that's also you have to ask basically Nandakumaran and see
Yes,
whether it's
sir. Yes,
possible.
sir.
So I really want to see more mathematicians to work in this field in our country. So I hope it will be the case. Yeah.
Yes, sir.
So thanks a lot for inviting me. Yeah.
Surely, I think our students will be very much inspired by your words, sir. Thank you so much. And you have explained it in a very beautiful and simple way, sir. It was very simply awesome, sir. Thank you.
And nice to hear that. Yeah. Okay.
Thank
So
you.
shall I leave?
Yes, sir. Of course,
Okay,
sir.
sir. Thank you. Thank you very much.
Thank you. Yeah, bye.
And I would request all the participants that please note our last session of the webinar series will be on 15th December, and it will be from 10 a.m. to 11 a.m.
Yeah, now
So
the
hope all of you.
feedback link is there in the chat box. I request all of you to fill it up. Thank you.
Yes. Thank you.